All right, everybody, welcome back. When last we left our intrepid investigators, we were talking about enolates of esters. So, there are a few reactions people use these for. And I'm a different breed of cat. I freely admit this, but I actually find some of these mechanisms fun. So the first thing we're going to do is talk about the alkylation of esters. And here's what the reaction looks like. You take an ester, an alkyl halide, and the matching alkoxide. Theoretically, here's what you get. And for those of you who were curious, 1, 2, 3, 1, 2, 3. It's an extension of the ester. Now, there's a couple possible hang-ups here. One of them being, couldn't the alkyl halide and the ethoxide by themselves make sweet, sweet Williamson ether synthesis love and just become an ether? And the answer is, yeah, that's a possibility. So a lot of times the way you can get around that is you do this in a two-step phase. So maybe a better way of writing this would be the ester, 1, the alkoxide, and 2, the alkyl iodide. So you do these in two discrete steps, and the product would be there. The reason you might want to do this is if you just have as your first step the ethoxide and your ester, the ethoxide and the ester, what you would form is the enolate. And then to the enolate, you could add your alkyl halide. So I realized I did all this. I'm on page 1, and I haven't shown you the mechanism yet. I just got done saying how exciting they were. So let's go ahead and take a look. So here's our ester. We use the alkoxide to deprotonate, form an enolate. Yes, the equilibrium would heavily favor the starting materials, but if a little bit gets through, that's all you need to form this enolate. And then reform the carbonyl. The enolate carbon does the nucleophilic attack, knocks off the iodine, and you get this. Now, one of the advantages, really, it's a limitation, is because this is SN2, you have to use a methyl or primary alkyl halide. Secondary or better, you would force into elimination. And you don't want to do that. All right, so why? Why, God, why do we care about this? Well, let's say, just for fun, that you had this. you wanted ultimately to get to here. To this carboxylic acid from this ester. And you're thinking, oh my God, that's impossible. Bricks without straw. Whatever are we going to do? Now, the answer to that, whatever we're going to do, is take a look over here at your product acid. So if you look at how the mechanism works up there, what you'll see is the acid comes from the CH, the acid group, the C double bond O OH, and that first carbon. All right? The rest of it is what you would add. So I'm looking at this and I'm seeing 1, 2, 3, 4, 5, 6. So the way I would do this reaction is 1, ethoxide, and 2, 1-bromo hexane. So that would actually get us here. Let me... That would get us to this ester. And to go from this ester to this acid, it's just acid and water. So that's one of the advantages of this reaction. This is one of the things you can do with it. All right, now let's get to the big one that everybody talks about when they talk about enolates and esters. What we're talking about is a Claisian condensation. There's that word again. Condensation because something is kicked off in this reaction. Dr. Weigel, doesn't that make SN1, SN2, Z1, Z2s, and pretty much every fucking thing we've done up until now? And a condensation reaction? Yeah, and like I've said, it's a really old nomenclature scheme. So here's how the Claisian condensation works. You start with your ester, and you react it with the ethoxide, and then some acid. Notice the 1-2 steps here. That's actually really important. Now here's your product. This is a beta keto ester. Beta because the ketone is at the beta position from the ester. Now you're looking at that and you're going, what? That makes no sense at all. Well, that's why I'm here to show you the mechanism. That's right, Brian. Uncle Bad Touch is here to help you out. All right, there's our enolate. Now you're asking yourself, there is no other electrophile in this reaction. To which I respond, oh, silly mortal. Yes, there is. There's more of the same ester. And what will happen here is this miraculous combination of enolate chemistry and acid-base derivative chemistry. Reform the carbon-oxygen pi bond, attack that carbon, open up the pi bond from the ester. What you get is this. With the oxygen anion and the OH that you just added. Now, this being a good little acid derivative, it's going to do what all acid derivatives do, which is reform that carbon-oxygen pi bond. It's a substitution reaction and knock off that ethyl ester. And that puts us here. Now, we're not quite home yet. All right, folks. I just realized I screwed up big time in this mechanism, and I'm 10 minutes in, and I don't want to start over again. So I'm fine up till here. I'm very sorry. Take it out on my teaching evaluations or my rate my professor. That's fine. So instead, the intermediate we get is this. That's better. And now, this oxygen anion is going to do what all little oxygen anions do when they're an ester, which is reform the carbon-oxygen pi bond. Remember, when you're dealing with esters and the rest of the acid derivatives, it is a nucleophilic substitution, not an addition. And now you are here. Now, there's one small problem here. And that problem is this. This proton right here in the middle. This puppy has a pKa of 9. Which means that ethoxide you just made, it's going to rip that proton off. And you're going to form another enolate. Now, does it really matter if the enolate goes through the ketone or the ester in this case? Honestly, probably it almost definitely goes through the ketone, but I don't care that much to make a fit of it. So you wind up with this intermediate, which is why you have to add the acid. You add the acid, you turn that enolate into an enol, and what you get is this. The beta keto ester. Well, we're out of time for right now, so tune in next time when we're going to talk a little bit more about Claisian condensations and some of what you can do with them. Until then, stay healthy, stay safe, stay sane, and stay hydrated.